Hello, everyone. Thanks for joining me. I'm going to be talking about Solr and HDFS. My talk's titled Solr and HDFS, Past, Present, and Future. I've been working at Cloudera for a couple years now, and my main focus has been helping integrate Solr with the rest of the Hadoop ecosystem. And one of the primary things we've done on that is allow Solr to run natively on HDFS the same way you might normally run it on a local file system. So I'm just going to kind of go into some of the things that we've learned about it, some of the limitations, some of the things that you can do. Should be fun. So about me, my name's Mark Miller. I'm a Lucene and Solr committer. I currently work for Cloudera as part of the search team as a software developer. Previously, I worked for a while for Lucidworks and a company called Newsbank before then. I used to do a lot of work in Lucene. I started with Lucene in 2006, became a committer in 2008. Kind of moved on to doing more Solr work in around 2009, and I've been doing Solr Cloud on and off pretty much since 2009. All right, some basics. Solr, I assume everybody knows what it is. It's a distributed search engine built on top of Lucene. HDFS, it's a distributed fault-tolerant file system, well known as part of the Hadoop stack. A lot of people in the past have wanted to run Lucene and Solr on HDFS. There's been a variety of attempts to do it, and nothing that's really taken off yet. We're trying to change that. So Solr on HDFS, a lot of people who are already using Hadoop, who are perhaps using MapReduce to build Lucene indexes, really like the idea of maybe being able to run Solr or Lucene on HDFS because, if you MapReduce build an index, the output is going into HDFS. It's kind of a pain to have to copy that to the local file system to use it. So wouldn't it be nice if we could just run natively against HDFS? In the past, people have wanted to do this or have attempted to do it, and the general response from committers and developers has been, it's just going to be too slow. You got to read and write over the network. It's never going to be fast enough. It's never going to be good enough. So, people have generally stuck to doing things like copying indexes in and out of HDFS and running them with Lucene or Solr on the local file system, which is kind of annoying to have to manage that. And if you have a very large index, it's pretty time-consuming to be copying it back and forth the entire thing. Basically, there's been a couple attempts, like I said, in the past to do this. The most successful so far, I think, is the Apache Blur project. We actually borrowed some code from them, their HDFS directory factory, or HDFS directory for Solr to kind of jumpstart our work rather than starting from scratch. We talked to them about whether it was okay if we borrowed this code, if they wanted to work on it with us. So far, they've kind of gone in their own path, and we're not really working together. But they did give us this nice code dump to begin with, which has kind of given us a good jump. Let's see. So one of the keys to how HDFS writes data is very important here because most of the reason that people think if you're going to run Solr on HDFS it's going to be really slow is because it's a distributed file system. The data is generally not going to be local. It's going to be off on the distributed file system. But in general, the way HDFS works is when you write data, generally you're writing it to a machine that has a local HDFS data node. And HDFS always will attempt to write a local copy first. So in non-failure scenarios, you're actually generally dealing with local data, not remote data, which is pretty important because that means in the default case, things are actually really fast. Whereas, in some failure cases, maybe then you're dealing with remote data. And so you have to come up with a solution for how to deal with that. So in general, because of that, like I said, when we deploy Solr and HDFS, we generally recommend that you put an HDFS data node on every single Solr node to ensure that all of your initial writes are going to end up local. Everything by default is going to be fairly fast. All you really need is an HDFS directory that knows how to. A directory in Lucene is like a pluggable implementation. You can write a different one for different file systems. You basically, just implement a couple read bytes, write bytes methods to get it to work. But what do you do when the data is not local? Your Solr node that's hosting the HDFS data node goes down. What do you do now? How do you fail over? The data isn't likely to be local anymore. So what Apache Blur did and kind of how they made this all work was they wrote a block cache, which is basically their replacement for a local file system cache. So if you use Lucene or Solr, the local file system cache is very important. That's what caches most of your index in RAM so that you're not hitting disk as queries are coming in. And so even more important than not hitting disk when you're running on HDFS is not having to hit HDFS. You want to have some sort of cache, but you don't really necessarily have a local file system cache, especially when the data is remote, right? So what Apache Blur did was they wrote, okay, we're going to write kind of a replacement file system cache in Java. It's not really easy to do and do it as efficiently as the OS file system cache, but they started something, they've been improving it. So we've been working on that. There is a problem. So this block cache, basically, it's basically in Java land. In general, it uses direct byte buffers to make sure that it's off heap, so that you don't have all sorts of GC issues. You're generally, if you have a really large index, you're going to want a really large cache. You don't really want this huge cache on the Java heap. So we use direct byte buffers to keep it off heap. There's a problem sometimes when you don't have local data. That means that there was a failure. Maybe you had to start up another Solr core and point it to the data for the node that went down in HDFS. You can use this block cache now to make sure that things are fast. As you're hitting HDFS, it's filling up the block cache. Future hits are going to be faster. But now everything is dealing with the block cache for speed rather than data being local. So it'd be nice to be able to get data local again. We don't have a good option for that right now. One option is to do an optimize on your index, which is going to rewrite the entire index, which means it's going to write one copy to the local data node again. And that's one way to get things local. Not a great one. We're hoping for some better options. We hope maybe in the future the HDFS team might add some sort of affinity feature. When data is not local, you can tag, hey, over time I'd like you to make this data local, and it can kind of in the background move it around and get it local again. But right now, the key thing for these failure modes is this block cache. I'll talk more about the block cache in a minute. So the starting piece and the main thing that we borrowed from Apache Blur is the HDFS directory. It's a fairly simple Lucene directory implementation. Like I said, for reading and writing bytes, it basically just uses the HDFS APIs to read and write bytes. It's really simple. It's actually fairly fast by default if you have local data, because the data is local. The file system OS cache is basically going to cache it. It's going to run through HDFS. But you can actually use this HDFS directory. If you have big enough buffer sizes, you can just use it raw, and things are really fast as long as the data is local. So that's kind of cool and surprising that it's relatively fast even with no block cache. But so you need the block cache to deal with these failure scenarios. It's actually also helpful when you have local data. Even though the data is local, if you're monitoring HDFS, you can generally see a lot of traffic through it, and things can be a little bit slower. Even though it's all local traffic, it can have an effect on other things that are using HDFS. So the block cache, even in the local scenario, kind of speeds things up, and it's a good idea to make a fairly large one. And so basically the block cache sits between HDFS and Solr. It's got a read side cache and a write side cache. The write side cache currently is turned off because it's a little buggy. We may just end up throwing it out. There's an NRT caching directory that can wrap a directory and does its own kind of caching. And that's probably better to use than the write cache that's built into the block cache. So it's mainly used as a read cache, really. So how is the block cache implemented? It's actually somewhat simple. It's a concurrent linked hash map is kind of the primary cache structure. And basically, this thing has a bunch of arrays of byte buffers that are called banks. So you can have a different number of banks, and each of these are put into the cache and keyed by this block cache key. And then so basically each of these byte buffers is like by default a little 8 kilobyte byte array. And so if you're storing a file, basically you'll get enough of these 8K byte arrays to fill up the entire file. And then when you're searching, you'll use the block cache key to pull back all the blocks you need to read enough of the file. So it works pretty good. The concurrent linked hash map has some really good concurrency. Under really high load, it may break down a little bit, but in general, it works pretty well. And then basically to handle concurrency, you have updates and reads coming in at the same time into the cache. It uses this little lock bit set to just kind of turn on the bit for whatever block you're currently dealing with, so you can keep things consistent. So like I said, it's pretty simple. It has some problems that I'll talk about, but in general, the implementation is pretty basic. So the global block cache. Initially, we first pulled in this HDFS directory factory, and it basically would build a block cache for every single index path that you were using. So Solr by default, if you only have one collection or one Solr core, it's going to be using one index directory usually. But sometimes it'll use more. Like during recovery scenarios, sometimes a replica will have to replicate the index from the master. And on some of these replications, it might have to spin over to a new index directory. And so the way things worked when we first put the HDFS directory into Solr was every single one of these directories that you used, which can be one or two for a single collection. If you have more collections, it's obviously going to be times the number of collections times basically 2 is probably how many block caches you need. And this ended up really being kind of a big problem because every time you create a new collection, that means you're firing up a new block cache. This block cache is using a lot of off-heap memory. You generally want your block cache probably to be gigabytes in size. So basically, you can't really pre-plan how big should the block cache be. Well, it depends on how many collections are you going to end up creating. And then you also have to account for this overhead of, okay, during recovery, it's going to possibly create even another block cache for every one of these collections. And so you have a limited amount of RAM, and you're basically going to have to kind of keep track and say, well, do I have enough RAM free to create another collection and fire up this new block cache? Everything may be working now, but is there enough RAM so that when a recovery happens and it has to fire up a new block cache, is it going to have the RAM to do it? Or right when I need to recover, is everything going to crash? And then there's other issues like cleaning up the block cache. All of this block cache memory is off heap with these direct byte buffers. And direct byte buffers are garbage collected or cleaned up basically in a finalizer, which is kind of indeterminate when Java is going to run that. And so you can have problems like you create a collection, and then you delete the collection, and you create another collection, and then maybe you delete that one and create another one. And you might still have the block cache for all 3 of those collections hanging out. And so it's basically just kind of a nightmare trying to pre-plan how much RAM, how big should these block caches be, how much RAM am I going to need over time as different collections are added. So we ended up adding this global block cache option to kind of fix all this. So now when you start up a Solr instance, there's a single block cache. Every single index shares it. There's mainly only benefits from this. One, so when you normally start a Solr installation, you think, how much RAM am I going to leave for the local file system cache? And you size your heap and everything else you're doing accordingly to leave as much RAM as you want for the local file system cache. Now with the global block cache, you can do something similar. You can say, okay, how much RAM am I going to give the block cache? Because there's only one. I can say I'm going to make it 8 gigabytes. No matter how many collections you create or what recovery happens, the block cache is just going to be 8 gigabytes. Everybody's going to share it. It kind of adds some more concurrent load. Now you're not kind of separating the block cache for each collection. So all the collections are going to be hitting it. So there's some extra concurrency hit there. But in general, now you can actually plan. So it's much better. So performance, I mean, this is kind of what everybody is generally interested in. Is this as fast as local file system? Am I going to take a huge hit? Why run on HDFS? Are the benefits worth it compared to the performance loss? So in general, I was pretty surprised when I first went to Cloudera. I thought, this is just probably not going to be fast. How is this going to be fast enough? But in general, performance is really good, especially on the indexing side. We can generally index, on a beefy machine, small documents. We can easily index 10 to 15,000 docs per second, which is actually generally what we see with local file system as well. So it's pretty close. On the query side, in general, and most of the little ad hoc testing I've done, you maybe take a 10 to 25% hit on performance, but it kind of varies. That's the general case. There's actually some more very specific cases where performance is even worse. We've seen some cases where people had a really small index, but wanted to support maybe 100 to 200 QPS per box on this index. and the block cache performance kind of starts to break down under this kind of heavy concurrent load. A lot of that due to the internal locking in the block cache, right? We have to do locking and concurrency control in Java, and it's just really hard to do that as efficiently as the OS file system cache, which basically almost gives you like lockless reads. So in most cases, basically, you're taking a small hit, and so you got to kind of determine, is it worth some of the benefits that I get? And so I'm gonna talk about some of the benefits of running on HDFS in a minute, and you can see, is it worth it for me based on these performance issues? And of course, over time, we're going to continue to work on improving performance. So tuning the block cache by default comes at 128 megabytes in size. That's probably too small. The main way that you change the size is you raise this slab count. It's kind of confusing how this slab count and the blocks per bank settings, which are two settings that you can control and config, relate to the internals of the block cache. But generally, you just normally think about it is each slab is by default 128 megabytes. So if you want to make like a 4 gigabyte block cache, you set the slab size to like 32 times 128 megabytes, you get like a 4 gigabyte block cache. So every time you add another slab, you get another 128 megabytes. The other thing is the block size. So this is the length of the byte array and the direct byte buffer. Currently in Solr, it's hard-coded to 8. That's just kind of what we inherited from Blur, 8 kilobytes. We found in some of the performance problems, such as that one where they had a really small index and they're trying to get hundreds of QPS on it, we found actually that if you lower the block size to 4 kilobytes rather than 8, for some reason that allows much more concurrency, it's much more efficient, it works much better. So now we've made this actually the block size configurable. I've been trying, I don't fully understand why dropping it to 4 from 8 has this effect. I honestly thought that if you have bigger blocks, that it would be more efficient. As you're reading through a file, you have to keep grabbing the next block from the cache, right? And so the smaller, the fewer blocks you have, the more of them you're hitting on the cache.get. So I kind of expected that larger is better, but in general, I've started to see that smaller is better. And there's some downsides to using a smaller one too that I'll talk about, but basically tuning is fairly simple because there's not a lot of settings that mean much. There's really the sizing, there's the block size, and there's a couple buffer cache sizes too, but I've been playing with those, and in general it doesn't help to change them much. So there's not a lot of tuning you have to do other than sizing, and in some certain cases changing the block size may help. So that's the HDFS directory and the block cache. Once you have both of those, you're running on HDFS pretty well, but you still have in Solr a transaction log. We use a transaction log for a couple Solr cloud features like real-time get, and if you have like a hard machine crash, you can replay the transaction log and make sure you don't lose any data on that single node. But the transaction log was also writing to local file system. So we pulled in the HDFS directory from the Blur project, and then we had to deal with the transaction log too. So basically, I re-implemented the local file system one in HDFS. It's really not a performance problem. You can write to it really fast. You're generally not reading from it much other than for near real-time get and sometimes for replays. We had some issues initially where the replay was really, really slow. The local file system implementation actually uses channels to be able to read and write efficiently, and when you read, to be able to see the latest writes immediately. And we can't do that with HDFS. So what we basically have to do when we're replaying to make sure we're seeing the latest writes is we have to keep reopening the file. And so what we were doing was reopening that file much too often initially, and replay was ridiculously slow. We started to run into this with customers who had like really, really large transaction logs, and now they're trying to replay them, and it would take like 3 days to replay like a 100 gigabyte transaction log, and it was a huge problem. So we've made that a little more efficient. We don't reopen as often now, and it's faster, but it's still kind of a downside. It's still slower than the local file system transaction log in these cases. But replay is kind of a less common scenario. It's probably fast enough now, so I don't think it's necessarily a big deal. The other issue is we have no truncate support in HDFS, and there's cases during recovery where things can fail, and we will drop the transaction log and start something new. With the HDFS transaction log, we can't drop it because we drop it by truncating, so we end up just having to replay the whole thing rather than truncating, and that can be a little slower too. But most of these issues are you're not going to run into normally, and they're not really going to be a problem. Most of the issues are still around the HDFS directory factory. And the transaction log we're not looking at too much, but there'll probably be some more improvements to come. So why run on HDFS if you have some of these trade-offs? One of the cool things is you can do some other features. One of them is this auto AddReplicas feature that we just added. So basically what this is we have in a Solr Cloud cluster, one of the nodes is elected the overseer. And we use this overseer node. If it goes down, another node is elected the overseer. We use this overseer node to keep monitoring the cluster state. And if it sees a shard goes down completely, all the Solr nodes that are hosting a shard go away, then what it can do is that data is still in HDFS, right? Like there was a local copy on that shard probably, and that's gone. But it also, by default, wrote 2 remote copies. So the index is still in HDFS. So what the overseer can do is say, hey, it looks like this shard went down, but there's still these other machines that are up. Let's recreate a new Solr core on one of those machines and point it to the existing index in HDFS. And so this is kind of cool because now you can actually run with no replicas if you want. You can run with just a single replica for each shard. And if you lose that replica, you get kind of like an HBase style failover. It's not going to be immediate. If you had replicas, normally it's fairly immediate. One replica goes down, you start hitting the other replicas that are up. But instead, so one replica goes down, there's going to be 10, 30 seconds, a minute, or whatever. The overseer is going to notice it. It's going to recreate the Solr core. It's going to come back. So all of a sudden, you can actually have an index that's spread across like 10 shards. And with this feature, if 9 of the shards went down, eventually maybe one node is now serving the entire index. Now, in some cases, that node's not going to be strong enough to do it. So there are some settings to say, like, only a maximum number of replicas can actually fail over to this machine, rather than, all of a sudden you have 1,000 shards on one node. But this is one of the cool features. So this is kind of just an example. If Solr and HDFS go down, there's 2 other copies on one of those other 2 nodes that are still up. So that's kind of cool. The future, what's kind of coming, that's what's there. There's some more stuff we're planning, though. So at Cloudera, we're building an enterprise data hub. This is basically the idea is all of your data lives in HDFS. The rest of the Hadoop ecosystem and all the other data management and data tools you have come to HDFS and deal with it. And so this is a lot of the reason we're pushing to run Solr on HDFS. We know there's some downsides to it, but if you're working on a Hadoop cluster and everything you're doing is already on HDFS, it's kind of annoying to also have to deal with this local file system issue. If you're running Solr on a local file system and all your other Hadoop world is living on HDFS, now not only are you monitoring HDFS and managing HDFS, but also on every node, the local file system. Do I have enough disk space? Am I running out of disk space on each node? And setting up monitoring for all of that. Whereas if you're already using HDFS, you already have management techniques for it. You already have monitoring set up for it. So for us, getting Solr on HDFS2 just makes everything more cohesive. It makes everything a little easier to manage. So we're going to keep pushing HDFS. We're going to keep improving some of these downsides that I talked about. We're going to keep improving the block cache. And so some of the things that are coming, the Apache Blur team has also hit some of the limitations of the block cache. One of the things that is really bad is like sequential reads, like I said, because you have to keep pulling more and more blocks from the cache as you read. If you have these long sequential reads, the performance can be pretty bad. So the Apache Blur team actually wrote a version 2 of their block cache that we're not currently using that has some changes that make it a little better. One of those things is variable size blocks. Rather than just 8 kilobyte blocks, you can have blocks that are variable sized. So one block can be the size of the file, so you only have to pull it back once from the cache, and all of a sudden you have the entire file right there in a byte array. It also optionally uses onSafe for direct memory management. One of the hot spots in the block cache when you're hitting it with high concurrency is you have to actually copy the byte array from the off heap space into the index input buffer. And this copy actually is a huge bottleneck. Whenever I run the profiler under heavy load hitting the block cache, this is one of the top methods. And so he basically uses, the guy who's doing this for Blur uses onSafe to do direct memory management and some reference counting to kind of share that memory location. Some other things that he did, let's see. he basically, that also using unsafe, lets him get rid of the direct byte buffer, which has a variety of issues. One of them is it has this little cleaner object that kind of hangs around and helps clean up the RAM once it's not in use anymore. And if you have a huge block cache, there's one of these for every single, plus some other overhead for every single direct byte buffer, and you can have thousands of them, hundreds of thousands of them, millions of them. Causes various GC issues. It means that even if you have a 4 gigabyte block cache, there's enough overhead that maybe really that's taking up 6 gigabytes of RAM. So using unsafe and doing this directly has kind of worked around all these issues for him. I hate to do it. You're not technically supposed to use unsafe. If I try to use it, someone will probably kill me in Lucene land. So we're trying to think of ways to work around some of these problems without doing that. And I have some ideas, and I've been talking to people even at the conference about some ideas. So hopefully we're going to be able to match this version 2 performance at some point, doing some things a little different than how the block cache works now. One of the other features we're going to work on, kind of similar to the auto AddReplicas feature, is the basically only having the leader write to HDFS, and then have all the replicas not write to HDFS, but just read the index and the transaction log from the leader. So one of the downsides right now, if you're running Solr and HDFS, is generally you're going to have replication from HDFS and replication from Solr. So it's kind of an explosion of the amount of data, right? You're not just going to have 3 copies of the data. You're going to have 3 times 3 copies of the data or whatever. So one of the ways around that is to use the add auto replicas feature and only have 1 shard rather than having any replicas, and then count on its kind of HBase style failover that's a little slower. But if you want replicas, that's not really the best solution. So what we'd like to do is change it so that the replicas are not writing, only the leader is writing. The leader will still send documents to the replicas so that it's still NRT that will populate the transaction log on the replicas. They'll just write to dev null, but their caches will be populated, the transaction log will be populated. Real-time get should still work. I think there's some trickiness that comes when one of those replicas is going to have to take over for the leader and take over its transaction log if a leader goes down. But I think most of the issues around that are solvable. And so what this will allow you to do is basically have 1 copy of the data. HDFS handles the replication. HDFS is much more actually hardened than Solr Cloud, so having it handle the replication is probably a good thing. And this is something I'm going to start working on really soon. So yeah, hopefully I have 2 minutes for questions, but that's my talk. Any questions? Yeah, go ahead. So currently it's only for HDFS. It certainly can pretty easily be extended to work with local file system. The only difference is if you get down to no replicas for a shard, you obviously can't fail it over because the data is not on a distributed file system, it's not available. But you can do, if you have 3 replicas and one of them goes down, you can easily recreate that replica on another existing node and it will just replicate from one of the replicas that's still up. So I don't know if I'm going to be able to work on that anytime soon, but I think someone will probably get to that soon, extend the code to work with local file system. Anything else? Anyone running Solr on HDFS now? Anyone using the upstream? This guy?
We're using it in a test environment. It works well. We have not had any issues. We're using it on about 3/4 of a billion records.
Right.
And it easily outperforms our existing production system that's not using Solr. And that has a high-speed SAN attached for its storage mechanism.
What's your motivation for running on HDFS? Right.
So it's more than just search. We have users that will be able to run SQL-like queries. So they're sort of a dual use case approach. It's like, well, if we're already going to have HDFS, why not use that, take advantage of it? So far, it's worked really well. So we're looking to push that into production in about 6 months.
Right. I mean, what we've found in general is it works.
Can you repeat his comments because we couldn't hear what he said? Or just summarize them, please, if possible.
Basically, he's using other components in the ecosystem, I think, and so it's kind of more convenient. I mean, the same reason we're pushing it for the enterprise data hub. If you're already using everything else that's using HDFS, dealing with the local file system is just kind of annoying. And we've found in general, performance and all the issues are like usually good enough. The only people that usually end up coming back to us saying they have performance problems, it's just because they're benchmarking it against local file system, mmap directory, and they're like, it's not as good. And still, usually it's good enough for them. People are just not happy that, hey, it's 20% slower. But in general, it's been good enough. Any other questions? Go ahead.
So you just used the word 20%. Is that a representative number?
Yeah, so I mean, we're planning to do some like, he asked if 20% is a representative number for the performance set. We're planning to do like some really intense official benchmarks with a performance team to really be able to give numbers that we can stand behind. To this point, most of the numbers we have are kind of ad hoc in what we've seen as the developers are testing and making sure things are fast enough. And so I'm just going by my experience. In most of the testing I've done, at least on the query side, when I benchmark it on the same hardware with local file system and HDFS, I usually see a 20% drop. Now, it depends on your use case. There's definitely corner cases that the performance is worse than that. In some cases where probably it's better. I've seen anywhere from 10 to 25%. So I like to say 15 or 20. And then on the index side, it's even less, I think. Indexing is pretty fast. You know, it's writing to HDFS just, you know, linearly straight along. There's not a lot to slow it down. There's some other things we're going to do to improve the read side performance too. HDFS has like this short circuit read thing where basically you can kind of skip the HDFS pipeline and basically get similar performance to a local read. We haven't done a lot of testing with that, but that should improve things. There's some other features that have come to HDFS recently that might improve things. So we're hoping to drop that, you know, down to something more like 5% hopefully. But it's always, I think, going to depend on your use case. I'm not sure we can get the block cache as efficient as like mmap directory in every case, but we're going to try. Yeah, one more. Yeah, we have some HBase. I mean, I skipped a lot of the other integration points. I just wanted to focus on HDFS because we only had like half an hour. But you know, we integrated. We worked with a company called NG Data to integrate with HBase. Basically, we have a Solr node that acts like a replica for HBase. It pretends it is. So data is asynchronously replicated to the Solr node, thinking it's an HBase replica, and we just consume that and create an index from it. And we also have integrations with Flume, with Spark, with MapReduce, with Sentry. We're basically pushing to not only run Solr on HDFS, but make it really easy to work with the rest of the Hadoop ecosystem. But I think I'm out of time, so thanks a lot.